Let's start. I mean, this part is just mainly a curiosity, especially the beginning. So let's talk about nuclear medicine, which, by the way, is the field that I've worked in for like 12 years before going back to university. So nuclear medicine, okay, is an imaging modality which is based on the physics of beta decay. Beta decay happens when a nucleus, the nucleus of an atom, has an excess of either protons or neutrons, and therefore it emits either an electron or an anti-electron to, let's say, rebalance. So like in this case, we have a nucleus with way too many neutrons. And what happens is that the neutrons become a proton by emitting an electron. So you say that you see that the charge remains, the total electrical charge remains the same, and an antineutrino, which is a particle that only theoretical physicists care about. And on the other side, if you have a nucleus with too many electrons, with too many protons, a proton will become a neutron while emitting a positron or an anti-electron. Let's give some example. If you have oxygen 15, normal oxygen is has 16 elements in the nucleus. If you have only 15, the oxygen will decay into nitrogen with the same number of nuclear elements, still 15, plus a positron and a neutrino. And while the stable hydrogen is, the stable oxygen is 16 elements in the nucleus. So you go from 8 protons and 7 neutrons to 7 protons and 8 neutrons. Fluorine 18 instead is, which is the most used one in nuclear medicine, has 9 protons and 9 neutrons and is a bit unstable, and it decays into 8 protons and 10 neutrons. Now, I've mentioned the anti-electron or positron. What is it? It's antimatter, which is basically the matter, the mirror image of matter, and every antiparticle as a corresponding particle. So like you have an electron, which has the anti-electron or positron, the proton, which has the antiproton, that go from positive electrical charge into negative electrical charge. And neutron has anti-neutrons that are still neutral, of course. Now, we were talking about nuclear elements. You don't have only nuclei, but you can synthesize, and this is often done in research laboratories, full atoms, or, well, I guess they never did molecules, but if you put an antiproton and an anti-electron together, they will form an anti-hydrogen atom that, for all that we have been able to measure in the last 30 years since we've been able to synthesize that, is completely identical from a chemical point of view. So its chemical properties are totally identical. It's perfectly stable, and until it interacts with matter, where they annihilate. So the thing about antimatter is that it cannot coexist at the same time with matter, and when they interact, they annihilate. And however, we have the famous relationship given by Einstein that mass and energy are equivalent, and we know that, well, in the classical world, we know that energy is always conserved and that mass is always conserved. When you go to the relativistic world, it turns out that is the sum of energy and mass that conserve. So in this case, we start with some matter and antimatter. They have some mass, even if they are at rest with no energy whatsoever. If they disappear, some energy must come out of that. It turns out that when you annihilate an electron and an anti-electron, you get two gamma rays. And given that all the classical laws of physics still hold, so conservation of momentum, conservation of matter, you get at least two photons. And due to the conservation of momentum, they must be back to back. Because if one is traveling in one direction, the other one must be traveling in the exact opposite direction. So that the total motion is still zero, because you had no motion beforehand. So what happens when you have a nucleus that emits a positron? This positron walks around in matter. It has what's called technically in physics a random walk. It moves around because to lose all the energy that it was emitted with, and then it stops. When it stops, it generally picks up an electron, and they start rotating, not like an atom where the mass is at the center and the very light electron is around. Here, the two masses are equal, so they turn one around each other. And they get so close that they annihilate, and the average lifetime of that process is 0.1 nanosecond, so almost instantaneous. Again, to summarize what I said, the mass energy sum is conserved, the momentum is conserved. So it happens that you get two photons that are identical in energy, because the total energy must be conserved, and they are identical in direction, so they are at exactly 180 degrees, and they have a very specific energy. So you're able to detect them quite well. This is just a summary of the whole process. And how do you exploit that? With a machine which is called the positron emission tomography. What happens? You have a nuclide inside the body that emits positron. The positron annihilate, and they emit two photons back to back. You put around the patient a ring of detectors. You tell the detector to record when two events, two photons of one specific energy happen in exactly the same time, and you get, therefore, given that you know that the two photons are exactly back to back, you can just draw a line. And you know that the emission should have happened along this line. What this means is that this is a tomography, a completely standard tomography. You just collect the data, and you can reconstruct back an image exactly like you did with CT, using the same algorithm. And yes, that's the core of the modality. The big difference is that with CT, you shoot rays and you see how many go out of the body. Here, instead, you have a radioactive source within the body. You need to stop these photons. These are gamma photons, not X-rays. What's the difference? Actually, they are the same things. The name comes, the distinction comes from when they were discovered, and X-rays were generated from the X-ray tube, while gamma rays were happening in nature, and but they are still very high energy photons. It also happens that gamma rays coming from nuclear decays are much higher energies. We have talked about kilo electron volts. An X-rays that we've seen goes up to 100, 140 for human use. Gamma rays for medical application, well, gamma rays in general start from 100 kV up. And indeed, in positron emission tomography, the energy of one photon will be half the electron mass. No, sorry, the exact electron mass, so 511 keV. You need to stop these high energy photons, so you need these very dense crystals that also need to be robust, transparent, because otherwise they don't transmit light. Small, because when you have a photon coming into your crystal, your spatial resolution will be limited by your crystal. And fast, because you need to measure coincidences within a nanosecond or so. Now, I've mentioned that we have these radioactive isotopes inside the body. And where on earth are we getting these substances that emit positrons, which is antimatter? What we use is we can produce these nuclei with some nuclear reactions using a cyclotron. I don't know if you've seen them. It's basically a magnet, a very big magnet that exploits the fact that using the Lorentz force, a charged particle will move in a circular motion. Even when it's accelerated, it still rotates with the same angular frequencies. So if you put two, these are so-called Ds, that keep on changing electrical polarity with the same frequencies, every time that the particle will go out from this half circle to this other half circle, it will be kicked and accelerate, even very slightly, but one turn after the other, you will get higher radius, but very high speed. That's an historical cyclotron, an old one with very high, took quite a lot of space and mass. This is what you get in your average hospital. It's compact. It's like 2 by 2 by 2 cubic meters. And that's including the anti-radiation shield, because you are accelerating protons, which is something that causes lots of radiation. The beam itself is very radioactive. And it will also create radioactive sources all around it. It just uses 55 kilowatts of electrical powers. It weighs 20 tons. It's self-shielded. So it's like, I don't know, probably half of the weight is water, paraffin, and lead to shield the different kind of radiations that come out of that. And it's, by the way, relatively cheap. It's like 1 or 2 million euros. It will last 20, 30 years, and you don't have too many of them. Well, in Milan, there are quite a bit, but we will see in the next slides that it's something that you can do a logistic. You have a couple of centers producing for multiple hospitals. So it's not the highest cost of nuclear medicine, even if you think having particle accelerator in an hospital, that's probably super expensive. Actually, that's not the most expensive part by far. How do you produce isotopes? Like, the most common way is that you accelerate a proton, which, by the way, is just hydrogen. So you literally buy a bottle of hydrogen and you put the gas in the accelerator, accelerate it with your cyclotron, and then you bombard a target of the material that you want. In this case, to produce fluorine-18, which is the most common used isotope, you bombard oxygen-18, which is a natural isotope of oxygen, but it's just like 5% of natural oxygen. This high-energy proton will kick out a neutron. It's called spallation. It's literally like mechanical substitution with a two high-speed balls. And you start with 10 neutrons and 8 protons, and you end up with 9 neutrons, 9 protons, and one neutron that has been kicked out. What are the most used PET isotopes for positron emission tomography? Fluorine-18, which has an half-life of 110 minutes. Half-life is the time in which the amount of radioactivity you have becomes half of that. So you still have it afterwards. And this is like 2 hours. And you can actually develop a logistic chain with that. There's a center in Monza, by the way, in Bicocca, in San Gerardo, which is co-owned by Bicocca and an accelerator company, and they sell radioactive isotopes to most of northern Italy, not to the Milan area. You can produce like a lot of fluorine-18 very early in the morning, ship it. After 3 hours, it gets to Venice, and they still have enough left for all of the day, the clinical day, which probably will be the first half of the day, not all of that, but you can use that. Carbon-11 was very used for because carbon is the base of biological life, so you can really bound it to lots of molecules. We've seen later what I mean by that. It has an half-life of 20 minutes, so you cannot really move around with that. Then there are some nitrogen-15, it's 10 minutes half-life, so you need to produce it where you use it. Oxygen-15 is 2 minutes, so you really need like a straight pipe from the cyclotron to the patient, which do exist, by the way. It's kind of research only, but it's used. Now, I've glossed over one thing up to now. I kept on talking about these radioactive isotopes, but why would you care about fluorine-18? We actually don't care about fluorine-18. The interesting thing that you can do with these isotopes, which are nuclei of an atom, is to bind it to a molecule of interest. So if you are able to develop a chemical reaction that does it, you can attach this isotope to a molecule of interest. And by molecule, I mean really anything. I was mentioning before oxygen-15. You can bind oxygen-15 with another molecule with another atom of oxygen, and you get the oxygen gas, and you just see where the oxygen gas goes in the body. That's really straightforward conceptually. And you can go all the way from there, the easiest chemical compound in the world, oxygen, all the way to an antibody or a peptide, so a very long, a super complex chemical structure. You can do anything in between. So the point of nuclear medicine is getting a molecule of biological interest, which is a huge issue for the chemists that need to develop that. And using positron emission tomography, you can track from the outside where the molecules are going. What happens is that you get in the cyclotron your isotope in a very simple chemical form, like when you produce fluorine, you get a fluorine acid, and then some automated mechanism shift all the radioactive product, which is really, really radioactive, is a monster quantity. You put it inside this shielded container. There are some automated chemical reaction modules that bind it to the chemical of interest. And that's something, due to the decay times, that to make sense needs to happen in less than an hour. Or if something is truly important, you can accept 2 hours or 3 hours, but something to that order, not anything that takes any longer. So what do you do in practice? This is like 90% of the studies that are done in hospitals since the early 2000s. That's the study of metabolism. You bind fluorine 18 to the FDG molecule, which is an analog of glucose. Glucose is sugar, and it's the basic form of energy for all cells. And so you're able to see which cells in the body are active and how much they're active. And that's the kind of scan that you get. By the way, notice the very poor imaging quality. And you have some unspecific findings like the bladder. Anything you inject in the body ends up in the bladder 90% of the times. Otherwise, it ends up in the liver, which, by the way, is here. And then here you have the kidneys filtering out the whatever in the blood, so including also the sugar goes there. But what happens is that in general, cancer cells are super active, and so you can spot them pretty well. In this case, we can see 2 spots. And yes. That's another application is cardiology. That's a double application of nuclear medicine. Here you do 2 scans to a subject. One is with rubidium-82, which is very popular in the USA. It's an atom, not even a molecule, that just flows with blood. So you can see how much blood is arriving in the cells. Now, this is not trivial. If you take a CT scan or an MRI scan of this heart, you don't see if blood is arriving or not. The shape is identical. So that's one of the main concepts of nuclear medicine. You see function, you don't see anatomy. By the way, the resolution is terrible. So you're not even attempting to see anatomy, but you can see function pretty well. And in this case, you are able to see that the blood is not arriving to this part of the heart that's called the septum, which divides the left ventricle from the right ventricle, in a typical view that the cardiologists like aligned to the direction of the heart. But then you also do a second scan later with FDG, this analog of glucose, and you see that the cells are alive. This means that if you restore perfusion to the heart, it will start beating again in that part which now is compromised even under stress. If you had found that the cells there had already died, it would have been not helpful to reperfuse the heart. There's a big, that's a field from which I will give you some data. I've told you that in the previous slide, I've shown you that if you inject sugar in the body, you don't see much uptake. You see some in the liver, some in the kidneys, and that's mostly it. You see very, very little uptake in the muscles, in the fat, of course, in the lungs, which don't have cells that do much. But this image before was cutting up the head, and the head, this 1.2 kilogram of matter that we have here, when we are resting, when we are seated, when we are sleeping, is 25% of our energy metabolism. This 1 kilogram of matter amongst these 70 kilogram of the average human. Therefore, it actually uses lots and lots and lots of sugar. And indeed, if you do a PET scan of the brain, you see the opposite of what you see in the rest of the body, where you see nothing having accumulating sugar and only tumoral cells accumulating it. Here you see that all cells, that's the gray matter, are very active, while the cerebrospinal fluid, which is basically distilled water, doesn't do anything. But it turns out that neurodegenerative pathologies turn off very specific part of the brain. Like in the case of Alzheimer's disease, the parietal cortex, the cells start to die specifically in this region here. And we will see when you have a frontotemporal dementia, of course, cells start to die in the frontotemporal area. When you have Lewy body dementia, also the occipital area turns down. And so you are able to do an extremely precise differential diagnosis years before you have changes in the anatomy of the brain that you can see with the MRI. However, an extremely interesting property of nuclear medicine is that it can be used for research. That's a relatively minor application of the total number of scans, but I've told you that we can add an isotope to every molecule of interest if we find a chemist good enough to do that, and it might take 4 years for a single molecule. What you can do is you can then do lots of studies. These are, by the way, very old studies from San Raffaele, and I guess one or maybe two of these people went up to become Minister of Health. No, only one in this paper. But Cristina Messa, the previous Minister of University and Dean of Milano Bicocca, she was also a nuclear medicine physician from San Raffaele. The current Minister of Health is a nuclear medicine from Rome. So they were looking at how much blood was arriving to specific areas of the brain in people that were bilingual or monolingual, that they were doing that using water that just flows with blood, marked with 15 oxygen. But you can do also, that's still FDG. Here that's very old research. Now this is not popular anymore, and you can see it from the quality of the images that were published. You could see what were happening in subjects that were abusing cocaine and the normal subject when they were taking benzos afterwards, and they see with extremely high statistical power, despite this super poor image quality, that the response of the brain was very different. Another option was the fact that you can attach to any single molecule. So in this case, they were marking with carbon 11 an analog of dopamine to see the dopamine circuits in the brain. So in the 90s, the research in the early 2000s, the research about how brain chemical imbalances in the brain neurotransmitter was working was extremely developed. And like in this case, they could find in smokers how the dopamine circuit was responding before and after smoking a cigarette. Now, by the way, they did lots and lots of research about psychiatric disease, especially because in the 90s, the US president claimed that that would have been the mental health decade. And because, there has been lots of theory about chemical imbalances being the cause of lots of mental health condition, and they were not successful in if you give an antidepressant like a SSRI to someone, you can see that the serotonin receptors in the brain change behavior massively with PET. You see the occupancy of the receptors changing. You can actually quantify that numerically, how many receptors are available before and after the psychiatric treatment. But if you look at the serotonin circuits, in normal people and in people suffering even acute major depression, you don't really find results. So apparently there's some involvement because we know that the humor changes, but it's not as trivial as we hoped. Now, another thing that we can do I've shown you images, but actually when I say you can follow the tracer in the body, you can do it over time. You don't need it to do in a specific second. And by the way, most molecules have some kind of temporal kinetic attached to them, depending how long it takes to react with their intended receptors. Nowadays, for research purposes and even for clinical application, there are some meter-long or 2-meter-long scanners, and this is what happens when you inject FDG in the foot of someone, and you see blood going up, going in the lungs, then in the heart, the kidneys, in the brain, and then it accumulates over hours. So let's go to some properties. What do we get in these images? We get a map of concentration, a quantitative, so it's like a CT, there's a unit of measure, but this unit of measure is how much tracer is there for every unit of volume, cc or whatever. So maybe the interpretation is not straightforward, I'll come back to that. The scan time is around 20 minutes. PET scanners used to have 15 centimeters field of view, like from here to here. Nowadays we have 20, 25 on top of these very large that are just starting to be on the market. If you want the total body scan, you generally scan for 2 minutes for body position. If you need to focus on a single organ, like you have a cardiac study or a brain study, you just do 20 minutes on a single organ. Why do you do that? Because as opposed to CT, the emission of X-rays, or gamma rays in this case, is coming from inside the body. And to get low noise, low statistical noise, you need to accumulate as many photons as possible. And you have two ways to do that. Either inject more, but there are some radiation safety concerns, and we are getting very close to the maximum dose, by the way, or you increase the counting time. You have no other options, because even if when you inject a tracer, it will continue to emit radiation until it will decay, whether you're acquiring or not. So it's for research studies, you can go up to 1 hour or 2 hours to see the distribution of molecules over time, but this is very rare. The spatial resolution is around 4 millimeters. That's the intrinsic resolution of older scanners. Newer ones claim 3 millimeters, but the practical resolution, the effective one, used to be 6 or 7 with the older one and 5 with the modern ones, because as we said for CT, the higher the frequencies, the more the noise is amplified. And here you are even much more constrained by the statistical noise, the counting noise, not any kind of machine-related noise. It's really the number of photons that you counted. The radiation dose is nuclide dependent, given the decay time. The longer the decay time, the more you need to count. So we have around 10 millisieverts for an 18F study and 2 millisieverts for a carbonyl level study. The pros is that this modality is actual functional imaging. So we see whether what's happening in every organ, if the cells are active or not, if they are active, dead, more active than they should or whatever, if some chemical receptor is present or not. And there are some minor tumors that nowadays are very, very much studied in PET that don't pick up glucose, like to the prostate, they don't pick up increased level of glucose. And for that, you have a prostate-specific antigen, and you can inject that and follow that and see prostate tumors. Now, they tell you that PET is is quantitative. That's not 100% true. You do get a number, but to be able to interpret that number, it's most cases you cannot fully do that. Most likely it's semi-quantitative. In general, it's extremely sensitive. Sometimes it has issues with specificity, depending on the tracers. And what can we say about quantitative studies? By the way, the bad thing is that it's the most expensive form of imaging. A PET scan with FDGs, which FDG is a cheap tracer, is 1,200 euros reimbursement. It has a very poor spatial resolution, very high level of noise, high radiation dose. It's slow because we said that you cannot acquire it in less than 2 minutes. So you get motion artifacts in the heart and in the lungs and in the liver. You do get motion artifacts. Nowadays, with ultra-sensitive models, it's kind of possible to ask patients to hold their breath for 30 seconds and get a decent image in just 30 seconds. And 30 seconds breath hold is feasible, but 2 minutes, it's not. Especially because you're acquiring 90% of the cases is old people with some serious pathologies, because nuclear medicine, on top of some minor research application, is used mostly in oncology. Like 85% of the scans are oncology, and the rest is split half and half between cardiology and neurology. And you need contextual anatomical imaging. In the previous image, you could see where the liver was, but it's not that clear. It's very blurred due to motion. It's very blurred because the noise is very high. So what they have invented, and that was really the invention that changed the field of nuclear medicine in the year 2000, is that of hybrid systems. And they invented PET-CT, hybrid PET-CT. How does it work? You get a PET scanner with its bed, and you physically put a CT in front of it in the same machine. Given that the bed is the same with the same microcontroller for motion, you get the two images perfectly aligned, and that's it. Because that's an example of what I meant. That's the PET scan. And if I tell you to try to understand what on earth this is, there's no way to know it. I mean, okay, you're not experienced, but even if you are, it's not like that you know what you're dealing with, especially because we are in the lower abdomen. And so it's a very complex area full of lymph nodes, organs. So how do you know whether this is in the prostate, in the intestine, in a lymph node, or what? If you acquire contextually a CT, you have this image here. This image here, you don't know whether these are lymph nodes. You don't know whether they have a tumor or not. And here you say, okay, there is a problem here. Because otherwise, guessing the location from here, it's really super hard. Okay, so that's it for nuclear medicine. I will provide you in the next image analysis experiences some neurology images, nuclear medicine images, and that's it for this part. That's the last imaging modality that I will introduce. Any question?